Okay, welcome, wonderful people, once again. Let us try to look at the second part of Newton's second law expressed in terms of momentum. So we are building on the previous understanding of momentum and the vectors, and also showing the directions and the magnitude of these vectors. So they say in grade 11 we considered the effect of several forces acting on a body simultaneously. So this is something that you have dealt with in the previous grades, where you looked at the different forces in different directions having an impact on an object. That single force that has the same effect as all the other forces acting together is the resultant force, or the net force. So the net force or the resultant force is a single force, which is a combination of all the forces that are acting on an object. So they are represented by a single force, and this single force has the same effect as those that are acting as a combination, taking into consideration the magnitude of those forces and the direction through which they are heading. So they say consider a person pushing a box along a horizontal surface. The box is being pushed towards the east, or in the easterly direction. Newton's laws help us to understand the action and the consequences of these forces. Now, I'm not going to deal with many theoretical statements that are provided here, but what I want to make clear is the formulas that are provided. So one of the formulas that are very important for Newton's second law is expressed in terms of momentum is that the final velocity of a vector it's equals to the initial velocity plus acceleration multiplied by the change in time. We are trying to show you the equations of motion, and one of those equations would be the acceleration. If we rewrite this, making acceleration the subject of the formula, you will have, remember, Vf. If this goes to the other side, it becomes minus Vi, and all this is divided by the change in time. And therefore, if the net resultant force is equals to mass multiplied by acceleration, which we can write as, we know that acceleration is the final velocity minus initial velocity that are acting on a provided specificity of time, and therefore the net resultant force will be equals to what? So F net, in other words. Now remember what this is. I'm going to show you something here. Remember, if we multiply here, we will have mvf minus mvi divided by the change in time. And what is this? This is the change in momentum. So F net equals change in momentum over the change in time. And if we cross multiply here, we can say that F net delta t is equals to the change in momentum. Very, very important. So we are therefore saying we are expressing Newton's second law in terms of momentum. The equation for representing Newton's second law in terms of momentum will be this one. This is something worthy of noting, and I'm not going to read a lot of theory for you. That will be left for face-to-face explanations. For now, I'm just looking at the content and just trying to answer the questions. Now, let us look at something in here. There's a problem that is provided for us here. They say when a rocket is 30 kilometers above the ground, it has an upward velocity of 10 meters per second. Very good. A booster rocket is fired downwards, resulting in a net force of 6,000 newtons being exerted upwards on the shuttle. The time it takes for the booster to leave the shuttle after being fired is 2.5 seconds. If the mass of the shuttle is 2,000 kilograms, calculate the velocity of the shuttle immediately after the booster is fired. Now, one of the most important things is to make sense of the statement, write down the data that is required, and see the appropriate formula that is required for that. Now, we're going to look at this with a very slow way of talking. When a rocket is 3 kilometers above the ground, very important. So, let's say this is the ground, and the rocket is 3 kilometers above the ground. So let's just have a rocket. I don't know how to draw up that rocket. So the distance here, we can say it's 3 kilometers above the ground. It has an upward velocity of 10. So let's say the initial is 10 meters per second. Very, very important that we understand this. So it is going upwards. Remember, we are dealing with a vector quantity here. Right. A booster rocket is fired downwards, resulting in a net force of 6,000 newtons being exerted upwards. So what is happening here, as the rocket is going up, a booster is fired downwards, giving this rocket an upward net force of how much now? 6,000, because it goes up. So this is the action reaction pair, but we will look at that in Newton's third law. So the object, the rocket is going up, and as it is heading up, there is a booster inside of this rocket. So when a thrust force is being exerted on the rocket by a booster, the booster is going down, but it is exerting an upward net force on the rocket of 6,000 newtons. So the rocket has a net force of 6,000 newton in the opposite direction. So F net, let's say, and remember they said upwards, so this is F net, it's 6,000 newton. Remember, a force is a vector quantity upwards. Sorry, this is 6,000. Right. The time it takes the booster to leave the shuttle after being fired is 2.5 seconds. So we have the change in time, which is 2.5 seconds, from 0 to 2.5 seconds. If the mass of the shuttle is 2,000 kilograms, we have the mass, which is 2,000 kilograms. This is the mass of the shuttle, not the mass of the shuttle together with the booster. No, just the mass of the shuttle. So meaning we are just interested here, or we are provided only with the mass of the shuttle, not the mass of the booster, because the booster, remember, when it goes down, it provides a thrust force in the upward direction. So this mass is only the mass of the shuttle, not of the shuttle and the booster. Right, calculate the velocity of the shuttle immediately after the booster is fired. So which velocity are they looking for? The final velocity of the shuttle. So what is it that we can do? We can play around with this. This is very, very important. So what we can say, okay, F net equals change in momentum over the change in time. But we know what this change is. This is m Vf minus Vi over the change in time. Very important. We have the net force, so let upwards motion be positive. So we will just take up be positive, because it is very important that in physics we always specify the direction. We're taking up as being positive, so that both the net force and the initial velocity will be positive. So we will have the net force of 6,000 Newton. What is the mass? It's 2,000 kilogram. Do we have the final velocity? No. Do we have the initial? Yes, that was 10. Do we have the time? It's 2.5 seconds. Now when you are in here, just cross multiply. 2.5 times 6,000 equals 2,000 into Vf minus 10. Sorry, 10 here. So when we are in here, we can just divide by 2,000, so that the three zeros on the numerator and the denominator can cancel. 2.5 divided by 2. This into this goes once because there's multiplication there. You will have your VF minus 10. Very good. Take to the other side. Equals VF. Note that this is going to be positive. Therefore, the velocity vector is also upwards. Something just worthy of noting. Now, let me just go to the calculator just to find out for you what the answer might be. So here we are. We just say 2.5 divided, let me just do this, divided by 2, and we add 10 to this. And what value do we get? Let me just do this. Let me check if everything that we are doing, it's in harmony with this. So what we're going to do there is the following. So we have let me check. 2.5 divided by, oh, sorry guys, I made a mistake here. I'm very sorry. We have 2.5 times 6. I'm very sorry. You see that I forgot to write that multiplication of 6 here. I'm very sorry with this. Very sorry, guys. So let me just correct this as quickly as I can. I'm very sorry. We should say 2.5 multiplied by 6. I'm very sorry for this. So let's just multiply by 6, and we will get 17.5. So 17.5 meters per second up will be the final velocity. That's exactly what we get. The final velocity is 17.5 meters per second upwards. So the direction always plays a significant role in this. Very important that we understand that, right? And then what is it that we do there? So we can go and say, let us look at test yourself, because those are the only problems that I see in here. I don't see any other. Oh, I think there are some. Yes, here is a problem. And one thing worthy of noting here is the following. It is very important that when we say the following, remember, let me just try to show you something here. There are some significant things that requires very close attention here, and these are the questions that will be mostly asked in multiple choice questions. Remember, we said that VF equals VI plus A delta T, and we are dealing with the vectors here. And if we make the acceleration the subject of the formula, remember we said VF minus VI divided by the change in time will be equals to the acceleration. And we know that Newton's second law says when a net resultant force acts on an object, that will be equals to the product of the mass and the acceleration. So where we see acceleration, we'll be writing that. Remember we said F net delta T M VF minus VI over the change in time. Multiply, remember there's a 1 on the denominator, multiply and multiply, you will get mvf minus mvi, this times this delta t, and we know this is the change in momentum. We have just seen this, right? When we have just seen this, it is very important to see that the net force is directly proportional to the momentum but inversely proportional to the time. Something worthy of note. Right, from there, let us look at an example. They say to us here, A car of mass 500 kilogram is traveling at a constant velocity of 5 meters per second. When the driver realizes that she is exceeding the speed limit, she decides to slow down. Very good. She applies her brakes 4 seconds. If a constant net force of 1000 newtons slows down the car during 4 seconds, calculate the change in momentum of the car after 4 seconds, the velocity of the car after 4 seconds. So this is very, very specific. The times are being specifically mentioned here. Let us try to read this for the second time. A car of mass 500 kilograms, so the mass is 500. We always try to write down the data. Is traveling at a constant velocity of 30 meters per second. Something worthy of noting. Right, the velocity is constant. Now I want you to check something here. When the driver realizes that she is exceeding the speed limit, she decides to slow down. So there is going to be a change in velocity. So let's take this 30 as the initial. So VI is 30 meters per second. Right. And then she decides to slow down. She applies her brakes 4 seconds. She applies the brakes for 4 seconds. So the change in time is 4 seconds. If a constant net force of 1000, so the net force doesn't change, so F net equals 1000 Newton, slows down the car during the 4 seconds. It slows down the car during the 4 seconds. Calculate the change in momentum of the car after 4 seconds. That is problem number A. Calculate the change in momentum of the car after 4 seconds. We know that the net resultant force is equals to the change in momentum over the change in time. We have a net force of 1000 Newton. We want the change in momentum for 4 seconds. Cross multiply. This would be equals to 1000 multiplied by 4, which is 4000 kilogram meters per second. Now remember, momentum has a direction. This is something worthy of noting. And one most important thing that I want you to realize here is the following. Let's read this again. A car of mass 500 kg is traveling at a constant velocity of 30. When the driver realizes that she is exceeding the speed limit, she decides to slow down. She applies her brakes for 4 seconds. If a constant net force of 1000 slows down the car, now, when the car slows down, tell me the vector direction of the net force. It has to be in the opposite direction. So I'm going to say F net in here, because this is in the opposite direction you are applying. We have a constant force in the opposite direction because when you apply the brakes, remember, you are slowing down the car. This is very important. So the net force has to be negative. So if the direction of motion was positive, the net force will be negative. So I'm going to use a negative there so that you may see why I'm doing these changes. Very, very important. And I know that the change in momentum is in the direction of the net force, because momentum and net force are vector quantities, and momentum will always be in the direction of the net force. So this will be what we have. We will have, remember again here, can I say change in momentum is in kilogram meters per second? Can I say that? Let's try to check this. Now check. F net, change in momentum over the change in time. Let's cross multiply. Change in momentum equals F net multiplied by the change in time. Are we fine? Yes. Change in momentum, this times that. And what is the SI unit of force? Newton. What is the SI unit of time? Seconds. So change in momentum cannot be in kilogram meters per second, it has to be in Newton second. Something secondly worthy of noting. So we're not going to say this, but we're going to say negative 4,000 Newton second. This is very important. Very, very important. And where is the direction? It is in the opposite direction of the car's motion. That is where the direction is. So for example, if the car was going east, the change in momentum will be in the westerly direction. So you just say negative 4,000 Newton second in the opposite direction of motion, or in the opposite motion of the car. Very, very important. So that would be the direction. So we will say negative 4,000 Newton second opposite to the direction of the car's motion. That's one thing that we can say. So please note those negatives, why they are there and why we needed to modify this. So we make mistakes and then we correct these mistakes so that you can see the differences. Something worthy of noting. So the change in momentum of the car after 4 seconds will be negative 4,000 Newton second, not kilogram meters per second. Something worthy of noting. Now in number B, they say the velocity of the car after 4 seconds. So they are looking for the final velocity. So I know, okay, that's fine. F net equals the change in momentum over the change in time, and when I cross multiply, the change in momentum equals F net delta T, and I know this is M VF minus VI F net delta T. That is fine. I can divide by mass and I can have VF minus VI. What is the net force? Negative 1,000. What is, in fact, let me write the SI units, Newton. What was the time? 4 sec. What was the mass? 500 kilograms. And then in here we will have VF minus, what was the initial velocity? That was 30, which is equals to negative 1,000 times 4, it's negative 4,000. Let's just say 500 in here, and then we will have VF is equals to let's see, negative 40 over 5 plus 30. This is exactly what we will have. So this would be, let's check, 5, 10, 15, 20, 25, 30, 35, 40. This will be negative 8 plus 30, which will give us a value of 22 meters per second. And remember that this is positive, so we will say in the direction of motion, or in the forward direction, or in the direction where the car is heading, or you can just say in the original direction. So this is 22 meters per second in the original direction. Something worthy of noting. Right. Now let me just take a pause and I will see you in the second part where we will be dealing with the test yourself problems.